On February 14th, 1990, a spacecraft 3.7 billion miles from Earth received an unusual command. Voyager 1 had already done its job. It had flown past Jupiter, past Saturn, past the outer edges of our solar system. It was leaving. It was finished. But an astronomer named Carl Sagan had one last request for the mission team. "Turn the camera around," he said. "Before it goes too far, take one more picture." What came back was an image so faint, so small, that Earth barely registered as a single pixel, a pale blue dot, a mote of dust suspended in a sunbeam, adrift in an ocean of black. Sagan looked at that photograph and said something that has traveled with us ever since. He said that Earth is a lonely speck in the great enveloping cosmic dark. He said everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that dot. He was trying to humble us, to hold up a mirror made of starlight and vacuum and ask, do you see how small you are? But here is what Carl Sagan did not know in 1990. Here is what nobody knew. We had not yet confirmed a single planet beyond our solar system. Not one. The first exoplanet around a sun-like star wouldn't come until 1995. The technology to detect them barely existed. The very concept of other worlds, orbiting other suns, remained almost entirely theoretical. Today, we have found more than 6,000 worlds, 6,000 planets around other stars, rocky ones and gaseous ones, frozen ones and scorched ones, water worlds and desert worlds, planets orbiting 2 suns at once, planets in the habitable zones of stars much older than our own. We have names for them now, catalog numbers. We have measured their sizes and their densities and their orbits. We have aimed our best telescopes at their atmospheres, and the universe has answered back with silence. That silence is what this video is about. Not the silence of an empty room, the silence of a room that should be full, that every equation we have says should be full and isn't. The silence that astronomer after astronomer returns to late at night, when the data has been processed and the models have been checked again, and the result still hasn't changed. There is a number that keeps astronomers awake at night, not because it is too small, because it is too large. We will get to that number, but not yet. First, you need to understand what we actually found when we went looking. The Kepler Space Telescope launched in March of 2009 with one mission stare at a fixed patch of sky. Watch for planets and count them. For 9 years, it stared. It recorded the faint dimming of 150,000 stars as planets passed in front of them. And what it found rewrote everything we thought we knew about how common worlds are. Kepler showed us that planets aren't rare. They're everywhere, around almost every star in every direction you look. Our galaxy alone, the Milky Way, contains an estimated 300 billion stars. Based on Kepler's data, scientists now believe there are more planets than stars, more worlds than suns. The universe is not empty. It is overwhelmingly, almost incomprehensibly full of places. If you spent 1 minute thinking about each confirmed exoplanet we found so far, 1 minute each, no breaks, day and night, it would take you more than 4 days just to get through the current confirmed list. And that list is the tiniest fraction of what exists. The actual number of planets in this galaxy is so large that it stops being a number and starts being something closer to a philosophical statement about reality itself. But here's where it gets strange. Of all those worlds, billions upon billions of them, how many are actually like Earth rocky, the right size, the right distance from a stable star, with an atmosphere capable of holding liquid water on the surface, with a magnetic field strong enough to deflect the radiation that would otherwise strip that atmosphere bare, with a large moon to keep the axial tilt stable over billions of years, preventing the kind of catastrophic climate swings that would otherwise make complex life impossible, with a gas giant somewhere farther out, playing gravitational goalkeeper against the asteroids that would otherwise rain down without end. Each condition, taken alone, sounds perfectly reasonable. Taken together, they begin to sound like a list of requirements for a very specific miracle. In the year 2000, a University of Washington geologist named Peter Ward and an astronomer named Donald Brownlee published a book called Rare Earth. Their central argument was blunt and uncomfortable. Earth is not typical. Earth is an outlier. The conditions that allowed complex life to emerge here required a combination of factors so specific, so unlikely to occur simultaneously, that the book's central thesis was simply this across the observable universe. It may have happened only once. The scientific community pushed back. Of course they did. The Copernican principle, the deep, foundational assumption that we do not occupy any special place in the cosmos, had governed astronomy for 500 years. Copernicus proved we aren't the center of the solar system. Hubble proved we aren't the center of the galaxy. Carl Sagan built a career on the conviction that life is ordinary, common, that the same blind forces that produced it here have produced it everywhere. But this is the part nobody talks about. The data that has come in since 2000 from Kepler, from TESS, from the James Webb Space Telescope has not been kind to that conviction. A 2025 statistical analysis from researchers at the University of California, Irvine examined 517 exoplanets against 8 key parameters for habitability, rocky composition, the right temperature, the right orbit, the right kind of star. The results were stark. Only 3 planets in the entire data set met all the criteria even under relaxed thresholds. Earth was one of them. And Earth, in that analysis, sat in the 69th percentile of statistical unusualness among all known planets. Think carefully about what that means. In a room of 100 worlds, you would be the strangest one there. Not the strangest by a little, by a lot. 75% of all the planets in that data set were classified as what the researchers call good star. Poor planet. The neighborhood is right. The address is right. The temperature from the star is right. And the planet itself fails every time, over and over, system after system. The door is set at the perfect height and nothing walks through it. In 2017, NASA held a press conference that gave the world exactly the kind of news it had been waiting for. They had found a solar system 40 light years away, a red dwarf star called TRAPPIST, one orbited by 7 rocky Earth-sized planets, and 3 of those 7 sat squarely inside the habitable zone. 3 worlds at the right distance, the right size, the kind of places that, in every science fiction film you've ever seen, you would land on and find something looking back at you. 40 light years. On the scale of the Milky Way, that is practically next door. If our entire galaxy were the size of the continental United States, TRAPPIST-1 would be roughly 100 feet from where you are sitting right now. And yet, to travel there in a passenger jet, flying in a straight line at cruising altitude, you would need 47 million years. That is what next door means in space. The excitement was enormous and it was justified. 3 potentially habitable worlds, closer than almost any candidate we had ever found. Scientists modeled their climates. Researchers argued over whether TRAPPIST-1e or TRAPPIST-1f had better odds of holding liquid water. For several years, TRAPPIST-1 was the answer to the question, the proof that Earth-like worlds existed in our own cosmic backyard. Then, the James Webb Space Telescope arrived. Webb is the most powerful observatory humanity has ever built. It can detect the chemical composition of an exoplanet's atmosphere by measuring how starlight filters through it during a transit, a technique so precise that it can identify individual molecules in a gas layer hundreds of light years away. Scientists turned it toward TRAPPIST one planet at a time. Stay with me. TRAPPIST 1b, no atmosphere detected. TRAPPIST 1c, no meaningful atmosphere detected. TRAPPIST 1d current data strongly suggests no atmosphere. 3 candidates in the habitable zone, 3 silences. This does not mean the outer planets are barren. It does not mean Webb has finished its work. Science is slow, and it is careful, and it is not done with TRAPPIST-1. But what Webb has shown so far is that even when you find the right neighborhood, even when you have 7 rocky planets, 3 of them at the perfect distance from their sun, the planet can still be bare, stripped, quiet. Here's what most people don't realize. TRAPPIST-1 is a red dwarf. And red dwarfs are not just the most common type of star in our galaxy. They make up more than 70% of all stars in the Milky Way. For years, that statistic felt like good news. Red dwarf habitable zones are tight and close, and planets inside them are much easier to detect. If red dwarfs could host habitable worlds, the galaxy was practically overflowing with candidates. But red dwarfs flare. They emit bursts of radiation so intense, so frequent, that any planet close enough to be warmed by their dim light is also close enough to be bombarded, stripped, slowly scoured. Over millions of years, over billions of years, the atmosphere peels away. What was once a world with weather becomes a rock with nothing to hold. TRAPPIST-1 may not be an exception. It may be a demonstration. In the summer of 2023, a team led by Niku Madhusudan at the University of Cambridge made an announcement that sent a charge through the entire field of astrobiology. They had been analyzing K2-18b, a world 124 light years from Earth, roughly 8 times the mass of our own, sitting inside the habitable zone of its star, with water vapor already confirmed in its atmosphere. In data from the James Webb Space Telescope, the Cambridge team found what appeared to be a trace of dimethyl sulfide DMS on Earth. DMS is produced by one thing: marine life, algae, phytoplankton, microscopic organisms in the ocean. If the signal was real, K2-18b had life. And it gets worse. In April 2025, Madhusudan's team published an updated analysis. The signal had grown stronger. A 3 sigma detection. The stories came back. Life on K2-18b became the kind of finding that scientists discuss carefully in print and argue about loudly behind closed doors. Then, a separate NASA-led team examined the same data independently. Their analysis, published in July 2025, found no conclusive evidence of DMS. Not a flat refusal, but not a confirmation either. And the laboratory experiments that followed made the picture even more uncomfortable. The methyl sulfide can form without life. Under simulated exoplanetary conditions, chemistry alone can produce it. DMS has been detected in comets, in interstellar molecular clouds, in environments where no living thing has ever set foot. The signal that looked like life turned out to be indistinguishable from chemistry. This is not an isolated incident. It is the shape of the entire search. A signal appears. Excitement gathers. Investigation deepens. Ambiguity returns. And then more investigation. And the ambiguity doesn't resolve, it expands. Not a definitive no, but never a definitive yes. Year after year. Telescope after telescope. The answer refuses to arrive. Sara Seager is a planetary scientist at the Massachusetts Institute of Technology and one of the leading figures in the search for biosignatures, chemical signs of life detectable from light years away. In 2025, she and her colleagues published a paper in the Proceedings of the National Academy of Sciences identifying 15 candidate biosignature gases worth searching for in exoplanet atmospheres. It was important work, rigorous and careful and significant. But Seager's paper also said something quieter, something that received far less attention than the list of 15 gases. There is no silver bullet biosignature. There is no single molecule, no single signal, no single spectral line that, if detected, would let us say with certainty something alive is there. Every chemical fingerprint we might search for has a non-biological explanation. Every atmospheric signature we could find can be produced by geology, by chemistry, by the physics of starlight interacting with rock and gas, and nothing else at all. We built the most powerful space telescope in human history. We pointed it at our most promising candidates, and our best scientists are now telling us that we may not even be capable of recognizing life when we see it. Now, pay close attention. Because we have been measuring the silence for 30 years now, from Hubble to Kepler to Webb, and the silence has not broken. And underneath all the data and all the models and all the careful scientific language, there is a question that gets asked in certain rooms, in certain conversations, by researchers who have spent their careers searching. What if Ward and Brownlee were right? This is the part that should keep you up at night. Not the failed atmospheres of TRAPPIST-1, not K218b's dissolving signal, not even the fact that our instruments may be too blunt to recognize what we are looking for. It is the math, based on Kepler's observations. Astronomers estimate there are approximately 300 million potentially habitable planets in the Milky Way alone. 300 million worlds meeting the basic criteria for liquid water. If each of those planets were a single grain of sand, you could fill an Olympic swimming pool to the brim. 300 million chances. 300 million addresses where the basic conditions for life are present, and not one of them has said a single word. That is the number that keeps astronomers awake at night. Not because it is too small, because it is so vast, so staggeringly, almost offensively vast, and so entirely, completely, and terrifyingly silent. The rare Earth hypothesis says the silence is not a mystery. It says the mistake was always in assuming that having the right ingredients means the recipe works. That water plus temperature plus rocky surface means life emerges. Ward and Brownlee argued that the path from chemistry to complex biology requires not just a habitable planet, but a stable one, an ancient one, a shielded one with a magnetic field and a large moon and a distant giant planet and a fortunate position in a not too violent galaxy. It is not enough to be in the habitable zone. It is not enough to have water. It is not enough to have the right temperature. You have to be lucky in 100 different ways, all at once, over billions of years, and not once get hit with something that ends the whole experiment. And luck, at that scale, may be a one-time thing. Go back to the photograph. February 14th, 1990, Voyager 13.7 billion miles away, turning his camera around for the last time. That pale blue dot, that lonely speck in the great enveloping dark, the only point of light in all the vast known universe where we have confirmed, beyond any doubt or ambiguity or contested spectral analysis, that life exists and looks up and wonders. Carl Sagan saw that image as a call to humility. He was right. But there is another way to read it now, one that Sagan, with his genuine and beautiful faith in the abundance of life, may not have wanted to consider. What if it isn't just a picture of how small we are? What if it is the only lit window on a very, very long street? We did not find the silence because we haven't looked hard enough. We found it because we looked carefully with our best instruments, at our best candidates, guided by our best science, and the universe gave us back the same answer it has given to every listening ear in history: nothing. And the most unsettling thought in all of modern astronomy is not that we might be rare. It is that we might be the only ones who ever got to notice. 3 things to carry with you. First, the search is not over. The James Webb Space Telescope has examined dozens of atmospheres out of hundreds of millions of candidates. The silence so far is not a verdict, it is a prologue. The instruments of the next decade, including the proposed Habitable Worlds Observatory, are designed specifically to find what Webb cannot. We are still, in cosmic terms, in the very first minutes of looking. Second, if Earth is rare, genuinely, measurably, statistically rare, then every living thing on this planet is part of something that may exist nowhere else in the observable universe. Not special in a comfortable sense, special in the way that a single candle is special in a room that has been dark for 1 billion years. Third, and this is the one that doesn't let go, Sagan called Earth a lonely speck in the great enveloping cosmic dark. He meant it as a warning against arrogance, but read it again from the other direction. A lonely speck in all that darkness, alone, and on it improbably, impossibly, for reasons we still do not fully understand, something arose that could look back at the dark and ask why. No other dot we have found has done that. Maybe the silence isn't a tragedy. Maybe it is a responsibility. Here's what I want to know if we received a definitive signal tomorrow, a real one. No ambiguity, no competing explanation, something alive and distant sending a message into the dark. Would you want to answer it? Or does the silence in some part of you feel like safety? Tell me below, because right now, in the direction of Voyager 1's long and lonely journey, we are the pale blue dot. We are the signal in the silence. And as far as we can tell, no one has heard us yet.